All right, so today we're going to talk about a concept that I'm sure you're somewhat familiar with previously, just friction. We know friction is where things kind of rub up against each other, and there is a force that's associated with that. So friction is a force that typically works to oppose the motion of an object. So if an object is rolling around the ground, we know, from Newton's first law, an object in motion stays in motion until acted on by a net force. Well, if we see some object, like imagine a basketball, and I roll it across the floor, it'll probably roll for a little while, especially if I'm on a court, right? We know different surfaces are going to have different amounts of friction, right? Imagine I took a basketball and I rolled it across a really thick carpet. Well, that would probably stop relatively quickly, versus if instead I rolled it across some smooth, like the smooth gym floor, it's going to roll longer. So the amount of friction is going to change, but we all know that eventually that ball will stop, and that is because there must be a net force on it, right? Because it's moving, so there has to be something to slow it down and decelerate, and we call that friction. That force is friction. So friction is a force that works to oppose the motion of an object. Friction happens because things are not perfectly smooth, and so you have things as they move across each other. Basically, what's happening, and we'll talk about this more when we get to energy. But energy is being taken from the ball, right? The ball has kinetic energy. Energy is moving from the basketball, in the example I gave you, into actually the floor. The particles or the molecules of the floor are actually moving a little bit. Moving a little bit more after it rolls across. So anyways, that's what friction is. Now, how do we calculate friction? Friction, the equation you see here is actually pretty straightforward. It may look a little weird, but friction is mu, which is what this thing here, this symbol I'm going to talk about in just a second, times N, when N is the normal force. So let me talk about what those are. What is mu and what is the normal force? First of all, mu, and I know the picture's a little grainy there as I blew it up, but mu is just a Greek letter. So a lot of times, in math, you start using variables, right? We know you use x, you use y, sometimes you use z. There's all kinds of variables that we use. T, y equals mx plus b, right? So anyways, point is we use variables a lot. Well, eventually you get to a point where, you kind of run out of variables to use in a sense, or at least standard variables to use. So it's very, very common and you're going to see it a lot in physics or in math that start using Greek letters instead of just using the typical ones. So typical letters that we use, which is the Latin alphabet or the Roman alphabet. So here, for example, you can see there's different letters here. I always used to joke that if I was going to start a fraternity, I would start the Delta Alpha Nu fraternity, which is just Dan, since my name is Daniel. But each of these letters, right, these are just Greek letters. And use some of them already, right? Theta, we know theta gets used for angles a lot of times. But this one here is mu, right? You see it right here. So mu, the way I draw it is it's like a U with a tail on the front. So it's like that. It's supposed to be an M. You may notice it's like there's one hump and there's the second hump, kind of. You kind of see it, right? Like obviously M has two humps. And the capital mu does, but usually we use lowercase mu. So this is just the Greek letter mu, mu. And we use that as what we call the coefficient of friction. So mu is going to be some number it's really a ratio of the it's really just a ratio of the forces there. So it's a ratio of you can see it on this slide back. My mouse is doing something weird where I don't see it. Oh, I know why. Never mind. Sorry. Okay. So if we go back here, you see mu is a ratio of the applied force to the resulting force. Mu is going to be a number. It's just going to be a number. It doesn't have units because it's a ratio. It's unitless. It's just a number, and that number seeks to sort of quantify how much friction is in a place, right? So, for example, if I apply 100 newtons of force and it results in the object experiencing a net force of 80 newtons, then the coefficient of friction there will be 0.2. But you don't have to worry about how to calculate it. I'm not going to ask you to calculate it. I will always give you the number. It's just a number, right? And so a lower number indicates there is less friction, right? So if you had like ice, if we were looking at ice and ice skates, the amount of friction there would be quite small compared to tires on a road. And it can go up to 1. Generally, you're not going to see anything above 1. Okay, so that is the coefficient of friction. So there's the first piece of the puzzle. How do we calculate the amount of friction in the present? You have the coefficient of friction. That's going to be an easy one because I'm just going to give it to you, right? We're not going to worry about measuring or calculating it. Again, it's not too hard, but it's just not something that we really do at the moment. But then we have to multiply by something else called the normal force. So let's, for a moment, talk about the normal force, because this is something you've probably never heard of before. What is the normal force? First of all, even the word normal. Is there a weird force? Is there an average force? Why is it called normal? Normal in this sense just simply means perpendicular to a surface. So you may see that later if you take calculus. You may use that, what we call the normal to the surface. But anyways, here normal just means it's perpendicular to surface. It doesn't mean it's like it's usual or anything like that. But what is the normal force? Well, let's think about for a moment here. Let's imagine we had you get the pleasure of seeing my drawing here. Here's a table. Right, that's what tables look like. And here's a book. Okay. Yeah, there we go. There's a book. See, there's the pages. All right, so you have this book here. It's just sitting on the table. That's all that's happening. What are the forces that are currently on this book? Okay, and you can, if you're thinking about it, hopefully there's one force that you are immediately drawn to, right? Because there's a gravitational force. So there's gravity is pulling down on this book. So if we were to draw it as a force diagram, maybe I would draw a vector, and we call that the weight. So the W here is the weight of the book. Okay, there's the weight of the book. But we have a problem here, because if this is the whole story, if this is the whole picture, then why isn't the book accelerating? I just said the book is sitting there on the table. You probably experienced this before, right? You can probably look around you right now and see if you have a desk in your room, or if you're at the kitchen table, you can probably see there's something just sitting there. It could be a coffee cup, it could be a book, whatever, but objects are not moving around you right now, or at least not any apparent motion relative to you. So what must be true? Well, if an object is not moving and it doesn't move at all, then what must the net force on the object be? Well, it must be 0. So what's the deal? Because I have a weight force pushing down, there must be some other force. There has to be some other force to balance this one out in order for this book to sit there and stay still, which of course we know that it does. This force is called the normal force. And it's exactly equal to the weight in this scenario right here, the normal force. But where does it come from? There's no gravity pulling up, right? It's not like there's down gravity and up gravity. That doesn't work. Gravity just pulls down. So where is the force pushing this up coming from? And it comes from the atoms of the situation, right? So very, very quickly, here we go. We have some atoms here. These are book atoms. We'll see how good my Microsoft Paint skills are. Yeah, they're okay. All right, so here we go. Here are the atoms of the book. But then there are also some atoms that are the chairs. Whoops, thought I was in my brush here. Okay, so here are the chair atom, or the table atoms, I guess I should say. I forgot it's sitting on a table. Now, what are they made out of? Probably, it depends on what you're sitting, what the table is made out of. It's probably some kind of wood. So these are probably carbon atoms, and I'm not drawing them correctly because I believe carbon has 4 valence electrons, but we'll just deal with it as we go. So right now, these two, so here the chair, right? The book is blue and the chair is black here. Or I keep saying chair, I'm sorry. Table. Usually when I talk about this, I talk about sitting in their chair, but given the circumstances. I just chose a book instead. All right, so what we have here is these two things are getting close. In fact, you probably assume, right, if you were just kind of use your everyday language, you would probably say they're touching each other, right? They're right on top of each other, touching. And certainly, they are getting close, right? They're definitely getting close. But to say they're touching is not true. They get very close, but what's stopping them from touching each other? Well, and when I say touching, I mean like literally being in the same space, the exact same space. And what's stopping them are these electrons, right? On the outside, we have electrons, and electrons have a negative charge. Well, these electrons right here have a negative charge. And these electrons down here also have a negative charge. So there's a negative charge here, and there's a negative charge here. So as they get closer, and these are constantly moving around, as they get closer, they repel each other. And this is called the electromagnetic force. And we'll talk more about it later, but the electromagnetic force, in the electromagnetic force, like charges repel and opposite charges attract. That's why the whole atom stays together in the first place, because you have these positive charged nucleus and you have this negative charged electrons. They stick together because of the electromagnetic force. So as these get closer, the electromagnetic force repels them from each other. And there is some distance, right? And we could calculate this later on, but there's some distance where these electrons are, where the force between them is equal to the weight pulling down on the book in general. So they get close enough, they start to they push against each other, and eventually they stop. So there's a really good video by Vsauce. I haven't linked it. I may put a link up in a classroom or something later, but you should definitely watch it. It's called "Why You Can't Touch Anything." And this is the principle. The idea is that that things can't actually be on top. Like literally, this electron can't be on top of the other electron because they repel each other, and the force grows exponentially. So as you get close, the force gets really, 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 really high, and so it gets so high that you can't actually force these things to be in the same space. There's some really interesting semantic stuff there, but I'm afraid we don't have time for it today. Point is, big picture here, is that there is this force pushing up called the normal force. And this is sort of like the sum forces of all the electromagnetic forces, the electromagnetic repulsion pushing up. And so they are at balance. And that's why this is not moving, and that's why it's at rest. Now, for our class, the normal force is going to be essentially equal, at least in magnitude, although in the opposite direction. It's going to be the same magnitude, the same number as the weight. And we already know how to calculate weight, so it won't be a problem for us. I will tell you that if you go on to take physics at a university level, you'll have these weird situations where, like, there's a box. I'm really bad at drawing, by the way. I don't know if you've noticed. There's a box on like an inclined plane here. If this was the scenario, the normal force would actually be in that direction, right? Because it's perpendicular to the surface, so it would actually go out that way. And then gravity would be pulling down this way. And, you get some weird things where you have to break up vectors. So you have to find the vector of normal force in this direction, the vector of the normal force in that direction, so you can calculate how fast it goes down the ramp or what components are there. But again, we're not doing that. I just want you to be aware that in this class, we're going to say the normal force is equal to the weight, but that's not always true if you have a surface that's not, the two surfaces aren't perpendicular or right up against each other. Okay, so now we talked about both parts. Now we can finally come to our kind of conclusion here. So we talked about the normal force. In this case, our class is always going to be equal to the weight, mass times gravity. So then you can really rewrite this equation as F equals mu times m times g if you want to. That's going to be the same, at least for this class. Okay, so we know how to calculate frictional forces. Let's try it out. Let's see if we can actually do it. Okay, so again, I know this lecture is a little bit longer, so that's why, and we're going to go over this example. That's why you don't necessarily have an assignment today, although you're more than welcome to go ahead and start working on the assignment. The plan is, because I think some of these questions are, I don't want to say like really hard, because they're not really hard, but they do take a little bit more than some of the other questions we've done. Like they're a little bit harder, I think, than a question we've done recently, at least. So anyways, today we're going over example. You'll see examples like this on the Schoology assignment. The Schoology assignment's a little bit longer. You can work on that tomorrow. And then really my goal is that you work on it tomorrow. You find some questions that maybe you're struggling with or problems that you really need help. And then on Thursday when we meet in person, it's just going to be a question and answer session. So basically I'll work out problems. If somebody wants me to work out, oh, I need help on number 3. Okay, I'll do number 3. Or somebody needs help on figuring out how to calculate the net force. We'll talk about that. Okay, so I'm going to show you an example here, and then hopefully, like I said, you'll come back with questions for Thursday's class. All right, so here we go. Scenario is we have a box with a mass. And I realized immediately as soon as I saw this, there's one more thing I want to mention about friction. And of course, it's on the other slide here. So there are 2 types of friction that we're going to be discussing. There's static friction and kinetic friction. Static means not moving or not changing. So static friction is the amount of friction that exists between an object between 2 surfaces. Friction is always between surfaces. So between 2 surfaces when they're both at rest. Okay, so imagine you're going to move a box, a really heavy box. You got to push it across the floor. You may find that it takes more force. In fact, typically, and you see there at the bottom, the coefficient of static friction, so the amount of friction in the static scenario where it's not moving, is generally greater than the coefficient of kinetic friction. And so you may have seen before, you may have felt before, if you're trying to push something that's kind of heavy, you got to push it. But then once it kind of gets going, it's actually a lot easier to push because, again, they're different amounts. So the static friction is generally the greater number, and again, static friction is the amount of friction that exists between surfaces when they're at rest. When they're moving, we use kinetic friction. So again, you just got to remember static is still, and kinetic means it's moving. And of course, you may know kinetic energy, moving. So we know hopefully kinetic means changing or moving. Okay, so now we can look at our problem. We have a box with a mass of 15 kilograms. Coefficient of kinetic friction is 0.38. The coefficient of static friction is 0.53. So the first question here, what is the minimum amount of force necessary to start moving the box? So because it's not moving right now, it says to start moving, we're going to be looking for static friction. So when we talk about coefficient of friction, mu is for the first problem here, because it's the static, going to 0.53. So let's see how much frictional force exists between the box and the floor. Okay, so we're going to use our equation. We're going to try to use our equation. Okay, there we go. Sorry. So the amount of friction, I usually use F sub F, so force of friction is going to be, we remember from our equation, mu N, which again is really mu times M times G. So in this scenario, the amount of frictional force is just going to be mu, which we said because the static is 0.53. My thing is really kind of messing up, and I apologize for that. Let me see if I can fix it real fast. This little device I used to write with, I think it's like 3 or 4 years old, and it's just kind of struggling. Okay, 0.53 times the mass was 15 times G, which of course we know now, hopefully is 9.8. All right, so again on my calculator, 0.53 times 15 times 9.8 is 77.91, and because of the force, it's friction. Sorry, it's not letting me write. Okay, I'll have to write with my mouse, which means it's going to get, the writing's going to get a lot worse. I apologize. 77.91, and that's newtons, 77.91 newtons. So that's the amount of frictional force that exists between those two surfaces. And so what that means is if you want to get this to move, right, if you want, in other words, the net force to be larger, you have to have a net force that's greater than 0. Obviously, you need a net force is what I'm trying to say. So this friction is always going to push back on you with up to 77.91 newtons of force. So if I were to push with 50 newtons of force, I would be met with, I'd be met with 50 newtons of frictional force back. But the point is, I would not be able to push it. Instead, I would need to push with greater than this frictional force here. So the very minimum would be basically any number greater than 77.91 newtons. So, if you want to write that out, I try to use it again, but it's not. So if you want to write that out, you might say, the force. All right, I'm just putting it away. It's unfortunate. Okay. So you would say that the force, whatever force you want to apply, has to be greater than 77.91 newtons. Okay, so that's the first question. Next one. Once moving, so again, that right there tells us we're talking about kinetic friction. Once moving, how quickly will the box accelerate if 800 newtons of force is applied? Okay, so we can use the information we had previously, right? So to find this answer, right, we're going to be looking for, we're really looking at what is the net force here. So we know that the net force is just the sum of all the other forces. So it's going to be the applied force plus the frictional force. F applied. And again, I'm sorry that I have to write this out with my mouse. I know it's not very good. But remember that the frictional force is always going to work against our applied force, against motion. So if I push with 100 newtons to the right, the frictional force is going to push with, we already calculated earlier, 77.91 newtons back to the left against me. So in this case, if I applied 800 newtons of force, the friction would work against me, so I'd have minus 77.91 newtons. So I would find my net force, because again, they're working opposite. I subtract them, 800 minus 77.91. I get 722.08 newtons. So the question asks, how fast would it accelerate? Once we know the net force, it's really easy, right? We just use Newton's second law. F net equals ma. So in this case, the net force. So if I want to find the acceleration, right, you can see I would divide both sides by the mass to get a by itself. I tried to reboot it again, but it didn't work. Divide both sides by the mass, and so you get, okay, so you get 700, so the acceleration is just going to be F, the net force, divided by the mass. So in this case, that would be 722.08 divided by 15 kilograms was our mass. 722.08 divided by 15. I get an acceleration of 48. 48.1 meters per second squared, which is a huge acceleration. So this is probably not very realistic, but that's what I got. And again, I'm sorry if you can't read that, but it says 48.1 meters per second squared. Okay, last question I think is the most difficult of the three here. It says, what force is necessary to accelerate the moving box at 5 meters per second squared? So we're kind of working backwards here, right? We want to know what is the acceleration, right? We're trying to figure out we're figuring out the force, but we know the acceleration. The acceleration has got to be 5 meters per second squared. So we should be able to use that to find the net force. So what I'm going to do is I'm going to start with I'm sorry, I tried it again. I should stop trying it. I'll put it away. I just hate how sloppy it looks, but I can't do anything about it now. All right, so we can calculate the net force here, right? Because the net force, if we use F equals ma, we know the mass, obviously, is 15, back up the top, and we know the acceleration we want is 5. So we can calculate the net force, well, pretty easily. It's just 15, this kilograms, times 5 meters per second squared, which I believe is 75, but I can double check since I'm a little flustered here. 75. So we want the net force to be 75 newtons. If I go back up here, you notice I wrote this little equation here. This isn't like an official equation. It's just a kind of it just makes sense, right? The net force is going to be the applied force minus the frictional force. Well, let's put this back into here, right? So we want the net force to be 75. So we have to get 75 newtons of net force. How much force? We don't know how much we'll have to apply. That's what we're kind of looking for. So let's just call it, well, I'll just leave it as F applied. The applied force minus, with the frictional force, again, it's never changing from this. Oh, no. It did change, didn't it? Okay. So I made a mistake here, which I can fix. So remember I said this was the, which friction is this? This is the coefficient of static friction. You can symbolize mu s if you want. But down here we were supposed to use, right? See here I put 77.91. That's not the right number. Because I should have used a different frictional force, right? This right here, frictional force, would be technically mu k times m times g. So the only thing I would change here is the coefficient, but that does matter because the coefficient of kinetic friction is 0.38, and that's why I need to do this in the first place. So let me go back here real fast just so you see the correct answer. Instead of 77.91, right, it should be, and this is what I'm putting in my calculator, it should be 0.38 times the mass, which was 15, times 9.8. And again, I'm sorry you can't read this, but 0.38 times 15 times 9.8. You just got to listen, I guess. 55.86. So again, that's what, so this should be instead 55.86. So notice it's less friction, which is what we would expect. So then whenever I calculate, I should have done 800 minus 55.86. So this number should actually be 744.14. Which means my net force here, again, this number would have changed. So this is kind of a mess, sorry. Final answer here for the acceleration should be 744.14 divided by the mass was still 15. So that would be 744.14 divided by the mass of 15. Yeah, so the actual final answer here would have been 49.6 meters per second squared. Okay, sorry about that. That should be correct now. So now back to here. We want to know what is the force necessary to accelerate the box at 5 meters per second squared. So the first part doesn't change at all, right? Because I just did mass times acceleration, got 75. So 75, and then we're going to take the force applied minus, okay, and now the correct force that it should be, again, not 77.91, that was right for the static, but for the kinetic friction, it should be 55.86. Okay, so then it seems it's pretty obvious now. To get the force applied, just add 55.86 to both sides. So 75 plus 55.86 is the total net force, the total applied force. The total applied force is going to be, I got 130.86 newtons. So that is the amount of force you would have to apply in order to get this to move at accelerate at 5 meters per second squared. Okay, so again, apologize for the mix up there, but again, it's always I don't mind to mess up. It's good because these are common mistakes that you can make, and hopefully, if you're watching this video or you're watching with me live right now, you saw, oh, that's something to watch out for. Make sure I'm using the right coefficient of friction because this was static up here, but once moving, see if it's moving, you got to use the kinetic friction. So again, sorry that my little pen thing gave out and the numbers are a little rough, but hopefully you can read that. Okay.